Welcome to this 15 minutes distant learning lecture on probability sampling techniques designed for 300 level undergraduate students, brought to you by Group 1 of MCOM 404 Educational Broadcasting. On this slide, you see a vibrant background with dice rolling, symbolizing randomness in sampling, along with abstracts, graphs, and icons representing data analysis. These visuals set the theme of our exploration on how probability ensures fair and unbiased research. Let's dive in.
What is probability sampling? Probability sampling is a core method in statistics where every member of a population has a known chance of being selected for a sample. This makes the sample representative of the larger population, enabling valid statistical inferences. Key features of this method include random selection, which eliminates human bias by choosing units purely by chance. It equally reduces bias by minimizing systematic errors, and it allows inference to the population so results can be generalized with measurable confidence. Looking at the illustration on the right side of the slide, there is a large circle labeled population connected to a smaller one labeled sample with an arrow marked 1 of n, showing the equal probability for each unit. This diagram underscores ensuring unbiased representation. Picture it this way, as a fair draw from a hat, but scaled up for research. Importance of probability sampling. First, it ensures representativeness. These methods create samples that mirror the population's characteristics, providing a reliable basis for findings. Secondly, it enables statistical inference, allowing calculations like margins of error and p-values to draw quantifiable conclusions. Third, it reduces bias by removing researcher subjectivity, leading to more objective results. And finally, it has broad applications in surveys, clinical trials, and market research where accurate insights are essential. The bar chart at the bottom compares probability sampling with a tall green bar around 80 to 90 units to non-probability sampling with a short dark green bar around 20 units, highlighting how probability methods yield higher accuracy and reliability. This visual underscores why we prioritize these techniques in rigorous studies.
Simple random sampling. In simple random sampling, every unit in the population has an equal chance of selection, and each is independent. It is the most basic probability method. The process uses random number generators like software producing sequences, or the lottery method where numbers are drawn from a hat. The formula is simple. Probability for any unit is 1 of n, with n as population size. For example, in a class of 30 students, to pick 5, write names on slips, draw from a hat. Each hat has 1 over 30 chance. On the right, there's a flow diagram with arrows from population to random selection to sample, and the fun illustration of a rolling dice labeled random. This captures the essence of chance, like rolling dice for fairness.
Systematic sampling. This method selects every KTH unit from a list after a random start, more structured than simple random sampling technique. To process this method, calculate K as n of n, which simply means population divided by sample size. Choose a random start between 1 and k, then pick every KTH unit. Then pick every KTH unit. Advantages of this method is it's easy to implement once K is set, and it is great for ordered lists, but always ensure you watch out for periodicity bias. If the list has a hidden pattern matching K, the sample might not represent the population. The diagram on the slide shows a list from 1 to 100, choosing K equals 5, a random start, and highlighting every fifth item in green arrows. This visual represents the systematic approach, like evenly spaced steps after a random kickoff.
Slide 6 centers on stratified sampling. Here, we divide the population into homogeneous subgroups or strata based on shared traits, then sample from each, proportionality or disproportionality. Proportional simply means sample size matches stratum size for accurate reflection. Proportional uses a fixed number per stratum, useful for small but key groups. Benefits include subgroup representation, preventing underrepresentation, and improving precision by reducing variability within strata. Example: survey university students by year, freshman, sophomore, junior, senior, and sample accordingly. The pie chart slices labeled freshman in dark green color, sophomore in green color, junior in light green color, and senior in pale green, illustrating dividing and conquering the population. This shows how strata make sampling more targeted.
Slide 7 talks about cluster sampling. This divides the population into natural heterogeneous groups called clusters, then randomly selects entire clusters and sample all, or some units within them. Stages include single stage with all units in selected clusters, or two-stage with subsample within clusters using simple random sampling or systematic. Advantages of cluster sampling include cost-effective for dispersed population, reducing travel, no full individual list needed. Drawbacks include higher sampling errors if clusters are too similar internally. The map illustration shows a continent-like shape with green highlighted regions, labeled sampling by groups. It visualizes clusters as geographic areas, like sampling whole neighborhood instead of individuals.
Multi-stage sampling. This complex technique combines methods in stages for large and dispersed populations. This method is in stages, where stage 1 is the selection of primary sampling units, PSUs, like states through cluster sampling. Stage 2 picks secondary units, like cities, while further stages narrow to households using simple random sampling or stratified technique. Application of this method. This method is ideal for national census or health surveys where listing every individual is impossible. The good sides of this method include its flexibility and reduction in fieldwork costs, with the potential contrary side like complex design and potential higher error. Looking at the slide, the pyramid diagram hierarchies from country indicated at the broad base to states, cities, and households at the narrow top, with arrows showing progression. This illustrates the hierarchical nature, moving from broad to specific units. Slide 9 centers on advantages, disadvantages, and comparisons between these sampling techniques. For simple random sampling, it is unbiased and simple for small populations but time-consuming for large ones needing a complete list. For systematic, it is easy for ordered lists but risks periodicity bias. Stratified, on the other hand, ensures subgroups, improves precision, but requires strata knowledge and complex if many. Cluster, on the contrary, it is cost effective for dispersed groups no full list but higher error if clusters are homogeneous. Multi-stage is scalable for large populations, flexible, reduces cost, but very complex with potential error buildup. For comprehensive understanding of these advantages and disadvantages, the bar charts rate them on a scale. For example, simple random sampling, high at 70, systematic at 80, stratified at 90, cluster at 60, and multi-stage at 80. It is understandable that the dark green bar represents advantages while the lighter green bar represents disadvantages. This visual helps compare efficiency and risks at a glance.
In conclusion, choose techniques strategically based on population, resources, and objectives. Always ensure you calculate sample size for statistical power. The application of this method is suitable for public opinion polling like Gallup. Use this to predict elections. Medical trails ensure comparable groups for treatment insights. Quality control in manufacturing inspect badges via systematic or simple random sampling. And lastly, market research helps businesses understand consumers and segment marketing. The illustration shows the people analyzing data with icons like graphs, a magnifying glass over a book, and collaborative figures, emphasizing practical impact.
From the concise explanations down to the illustrations, the charts, the images, the visual elements to aid your understanding. This course is designed to explore probability sampling techniques for better comprehension of 300 level undergraduate students across every tertiary institution.
Thank you for joining. We hope this course helps your understanding of probability sampling techniques and benefits your research projects.